Welcome to the latest in our series of programming languages talks. Today we have a guest speaker from outside of Google because not enough people from inside of Google are coming to me and telling me that they want to give talks. So everybody should come to me and tell me that they want to give a talk. Even if you don't want to give a talk, you should come to me and tell me that you want to give a talk. Today we have Adam Welk coming to us. He's a research scientist at Intel's Programming Systems Lab. He recently graduated from Purdue University with a PhD and has been working on transactional memory. And he's going to fill us in on all of the wonderful things that they're doing at Purdue with transactional memory. Adam.
Thank you. I've already been introduced, so I will only say this. This work is in collaboration with all the people that work in my lab at Intel and Programming Systems Lab. Their names are listed on the slide. And the title is, I think, somewhat bold, but that's really what we do there. We sort of cover the whole spectrum of issues related to transactional memory, starting with programming language constructs, semantics, and going to investigating possibilities for hardware acceleration of these constructs. So that's what I'm going to talk to you about today. I'm going to give some general motivation on why we even bother to think about new constructs for programming, for concurrent programming. I will talk about the construct that we propose and other people propose, and a little bit about their semantics, so how they behave in programs. And then I'll present our own version of how these things should be done or could be done, and then how we propose to accelerate them using hardware support, future hardware support. So just to give you a bit of motivation, let's just go through a small exercise of designing a concurrent data structure, a concurrent map. So we would like to have 3 operations. We would like to have different threads execute these operations concurrently, safely, so that there's no interference, there's no corruption of internal metadata. The operations are put, get, and remove. So Java used to do it that way, obviously using Java syntax. We just have synchronized methods. So we essentially say, if one thread tries to execute one of these methods, all the other threads have to wait, as this mutual exclusion. And that appeared to be not so great in the case when you had a lot of readers that wanted to access this structure concurrently. So let's say it was pre-initialized and there was an occasional write or remove, but the majority of accesses were reads. So there was a refinement on that proposed a while ago. And this is actually abstracted away version of what's now in the Java concurrent package and JDK 1.5. So the idea is that, well, let the readers try to do these things optimistically without synchronization, and only if we detect some sort of interference, then we'll try to fall back on having these things fully serial. So the code just got a little restructured because put and remove potentially could have some internal optimizations as well, possibly. But the gist is that we would like to have the reads more efficient. So now we get to how we use this map, and it works for simple operations. Obviously, if you have multiple threads executing puts, gets, removes, then it's all going to work nicely. But what if we want to do something more complicated, like transfer values from one map to the other? Then things start becoming a little more tricky because suddenly you have no good way to express this paradigm, and you have no way to say that the transfer from values between 2 maps is supposed to happen as a unit. So in this particular example, you probably would like to see some consistent value read by thread T2, rather than have it read things in the middle between when the transfer is happening. So in Java, using synchronized construct, the way you do it, you'd probably just enclose these things in global logs that would just guard these accesses and make them serial again. But this sort of comes back to the original problems that we have with the first implementation of the map, which is we're back to coarse grain. This concurrent thing with readers is not working anymore because we have global logs. But also in this particular example, 2 programmers wrote things independently, and they wrote the code that acquires logs in a different order. and thus they created a possibility for a deadlock. So this particular fragment of code can actually get stuck, just because you acquired locks in a different order. So this is the motivation why we want to do things differently, because what we really want to do is we want to just specify the desired properties. Rather than hard code the actual protocol for synchronization into the application, we just want to say, we want things to happen atomically. We just want them to be isolated from one another when different threads execute different pieces of code. So in this case, we'll just enclose these different operations that are by themselves atomic. We'll enclose them in sort of another bigger atomic block, and we'll hope that the runtime system will take care of everything for us. So that was the motivation, and I'm going to go into a little bit more detail of how these things actually behave. So the goals that we have is that we would like to have the ease of use of coarse grain locking, like in the first example that I presented, but at the same time, we would like to have the efficiency of fine grain locking. And at the same time, we would like to be able to compose things so that we don't lose the benefit of fine granularity locking efficiency, but you retain safety, so you don't have these nasty deadlocks or anything like that. So the inspiration for how to do this differently came from the database world, where you have this notion of transactions. They have certain properties, relatively high-level properties, and they're typically the ones that are mostly referred to are the ACID properties, which are again listed here. It's atomicity, consistency, isolation, and durability. But some of these properties do not make much sense in the context of a programming language. Like consistency had something to do with bringing or actually moving the database, the persistent state, from one consistent state to the other. We don't have such a notion in the programming language. Same with durability. We really don't make anything durable. Once the power is off, everything's off. So we can scratch these two properties from the ones that we really want to have, and that's what we really call the atomicity. So we sort of fold in isolation and the notion of database isolation and atomicity into the concept of atomicity that we want to have in programming languages. And so that's a very high-level view of things, but there are different flavors possible, just because you can provide different isolation and atomicity levels. And the reason for that is that we're operating in a slightly different context here. So in database world, essentially all computation was enclosed in transactions. So you couldn't have non-transactional computation. If you want to use atomic in a way analogous to synchronized in Java, then suddenly we'll still have pieces of computation that will be not enclosed in atomics. You'll be non-synchronized, non-controlled. And so you still have this possibility that there will be data races, which means that you will have accesses to shared data from inside and from the outside of these atomic blocks. And it's very, and I already said that, it's very true that programmers are interested in high-level properties like, let's make this isolate and let's not care how this is done. But for performance reasons, you may sometimes have to compromise that. And these are the reasons why you may want to have different flavors of these atomicity and isolation properties. The major division that we have right now is between weak and strong atomicity. And this is exactly, the example that I am showing here is exactly the kind of situation that I talked about before, which is that one thread is performing a computation that's supposed to be atomic. The other one is just operating on the same data, but a programmer forgot to enclose it in an atomic block. So then what happens? This is a perfectly legal piece of code, maybe not the best written code, but we still need to provide some properties for the programmer to understand the behavior. And this relaxation of the high-level abstraction comes in the second bullet, and essentially transactions have to resolve conflicts, and there has to be a mechanism that allows them to do this. And typically this is done by just redoing certain parts of computation, by rolling back the computation that went wrong and just redoing it so that in hope that it will actually go right the next time. And unfortunately, the effects of these rollbacks can become visible in this kind of situation. So I'll just walk you through an example of how this particular fragment of code could be executed under the weak notion of atomicity. So let's start with thread T2 reading just a field of an object bar. And let's assume that initially the value of this field is 0. Then we'll have a thread that's actually executing atomically a read from another field of another object, field x of object foo. Then thread T2 updates the same field that the atomic thread has already read. So the next read from the atomic thread will actually return a different value, just because the memory location has been updated, and so really nothing under this particular model, nothing really can be done. But it's unclear if this type of behavior is the most desirable one, because from some point of view, thread T1 may want to be completely isolated from everything that happens in the system, so it shouldn't see anything else that happens between it starts its atomic block and finishes its atomic block. When we proceed with the execution, we'll have atomic thread to update a field and object bar, and then we'll have thread that is not atomic to read the value from that field. Unfortunately, we have these nasty rollbacks. So on conflict, 3.1 may actually not successfully complete, its computation may be redone. But thread T2 has, in this case, already read the value that has been put into memory by thread T1. So now what do we do? It has seen a computation that conceptually shouldn't happen because it will be rolled back. So these are the problems that come with this particular isolation model, but this can be implemented relatively cheaply, which is not necessarily what we can say. This is obviously the abort. Which is not necessarily what we can say about a stronger isolation or atomicity model, which is strong atomicity. So in this particular model, we guarantee that all computation is isolated from one another. So regardless of whether a thread is executing within an atomic block or outside of an atomic block, no values are being transferred between these two threads. And we'll use the same example. Ooh, OK. That is not what I intended to show on the slide. The code fragment should be there. Let me think what I can do about that. OK, let's just pretend that it's there. Essentially, what will happen is that the thread will read the same values within an atomic block, rather than reading a value that has been updated by thread T2, which we cannot see at this point. And at the same time, thread T2 will see only the original value, will not see the value that has been put into memory by thread T1, but has not yet been committed. And I apologize for this quirk. So then even if the conflict happens, the isolation has not been breached. But again, as you can imagine, this particular model is much more expensive to implement. Yes? So the question is, what does it mean to be atomic if we don't know what's the granularity of atomicity? In that case, it's just a single operation. So essentially, the whole atomic block is seen by a thread that's not using this construct at all as executing instantaneously. So this is the notion. This is the notion of atomicity, of strong atomicity here. And there are several constructs that can be used for this style of programming. I'm not going to go into detail on exactly how they behave. I believe there actually has been talk in this series that discuss some of these constructs, like retry or else. But the introduction of these constructs is essentially required to make this thing usable in the real world. Because if you have full isolation between threads, then there's no communication. So you have to provide facilities that will allow you to at least to some extent pass values between transactions, or to support some form of condition synchronization. And these are the constructs that are on the slide, other than the generic atomic block, which is the retry construct, and the or else construct, which lets you choose different alternative paths of execution. And we haven't invented these constructs. We only adopted them to the Java environment because they have been previously introduced in the context of functional programming languages. So I think that's that sums up the sort of the language integration semantics part of the talk. And now I will discuss our own incarnation of the transactional memory system. So how these things are actually implemented under the hood. So how we make it actually work and perform. This is the overview of the architecture of our stack that we have built in the PSL. We support both Java and C, although my talk today is mostly definitely biased towards the Java portion of the stack. But very similar mechanisms are actually available for C. There are slightly different sets of challenges that you have to that you're facing when you're dealing with a non-managed language environment. So essentially, you have a transactions-enabled application on top of the stack. And below that, you have, in the case of Java, you have a VM, a virtual machine, and a JIT compiler that are aware of these extensions. And they'll be passing them. They'll be passing requests for this data tracking and coordination into the transactional memory runtime, which is implementing the gist of the functionality. And on the C side, we typically don't have runtime environments, so essentially everything is channeled through the compiler. In this transactional memory runtime, in our case, we can run it both on top of existing real architectures, SMP machines, but we also can run it on top of simulators so that we can experiment with hardware acceleration of our stack. So this is the most interesting part of this, I believe, of this architecture is the actual transactional memory runtime, and we just implement one flavor of possible. Well, it's just one possible flavor in which you can implement the whole transactional memory system. That has been backed up by a certain amount of previous work and profiling and these type of things that let us choose what we believe is the most efficient approach, at least for the application that we've tested. So we do in-place updates, which means that threads, when executing either within atomic blocks or outside of atomic blocks, they'll write directly to memory, rather than an alternative approach where they can buffer their writes and apply them all to memory at the point when the atomic block is finished. So I'm only going to concentrate on the approach with in-place updates. But that puts an additional requirement on the runtime system, which is to be able to undo the effects of computation, because they are already in the memory. So if the transaction violated the invariance, the atomicity and isolation invariance, it may have to be rolled back. So we need to maintain metadata information that will allow us to do that, and it's called undo log. It's analogous to the database, to the way that database transactions are being done. With respect to data accesses, this again was experimentally chosen as the best combination for the implementation. We do optimistic reads because we're trying to make the reads as cheap as possible, just because they tend to be more pervasive in typical Java applications than writes. So we essentially let the reads let the reads proceed and validate their correctness at the end of the transaction. So we hope that everything will be all right and we'll be able to commit the transaction. If that's not the case, then we'll have to roll back. On the other hand, we implement pessimistic writes, which means that we use exclusive locks to prevent concurrent updates to the same memory locations. And on writes, we update the version numbers so that the reads can then use them to validate themselves and check whether the whole transaction was actually valid. But because we use exclusive locks, there is a potential for deadlock. But this is not the deadlock that we've seen before, which would be sort of triggered by the programmer. It's deadlock that may happen just because of the choice of the implementation. So we essentially were obligated, and we do resolve it internally. So we can break. In the transactional world, it's easy because we can break the cycle of the deadlock cycle and just redo one of the transactions, and the rest of the transactions can proceed. But we also have that functionality in our system. So how do we really translate this atomic thing into the actual code? This is sort of a very abstract view of things, but we essentially start a transaction and then commit the transaction when the atomic block starts and then finishes. And we track all these data operations that happen inside of on the shared data that happen inside of the atomic block. So these abstract procedure function method names, TM write and TMWR, which is TM write, and TM read, the roles are explained here as well. The write operation is supposed to acquire a log and update the undo log. The read operation is supposed to record the version number so that then they can be compared to the version numbers that are present in memory to facilitate validation. Because deadlocks can happen, we have to be prepared to handle them. They can happen at a point when we write. So we need to have a mechanism to actually return control to the beginning of the transaction, undo the effects of this transaction, and re-execute it again. And that's language dependent. That's why it's so abstract. And C-code, in the case of C-code, we can use long jumps. In case of Java, we actually utilize a modified sort of exception-like mechanism. So essentially, you can walk the stack using similar mechanism to the one that's used for Java exceptions. So how this tracking, locking of things is being done? It's being done by introducing certain data structures in the runtime. There are some data structures that are required per piece of data, which, for example, in Java would be per object or per field. It depends on what we choose. And there are also some that are needed per thread or per transaction. So per data, we have a transaction record, which essentially contains information about the state of this piece of data with respect to the state of the transactional execution. And it can either contain a version number, it's a pointer size field, and it can contain either a version number or a log in case this data item has been written. Per thread, we maintain this sort of piece of metadata that describes the state, that directly describes the state of transaction. And it also contains pointers to additional metadata, which is the undo log, and two additional data structures that are used for the purpose of validation. And there will be an example that hopefully will make it clear what they're used for. Yes?
So how do you define a piece of data? Is it an object or individual member of an object?
Yes. On the next slide, there's a little sort of presentation of what we can do, and we can do both, essentially. So the default actually is the granularity of data management is an object. So essentially we embed the transaction record into the object header. So we extend object header by one pointer size field, and then we have direct access to it when we have a reference to an object. But we also allow word level granularity, and that's for Java. It's just this. It's field level granularity, but it's also used for C because in C, you don't have a notion of an object, right? So you have to either do this on the per word basis, per memory word basis, or on a per cache line basis. And so in this case, you actually have an external map that maps addresses essentially to the table that contains the transaction records. In Java, it would be hash codes or equivalent of hash codes rather than addresses, because obviously GC is not really, using addresses in Java in presence of copying GC is not really good because they can change in the course of the program. But yes, we do support both. So this is an example of how this actually works, how to put all these things together, this metadata, this transaction record, and again, hopefully this will make it much more clear on how this whole mechanism works. So we have two threads. Both of them are actually enclosed in their operations are enclosed in atomics, and essentially what they're trying to do is the thread T1 is trying to copy values from one object to the other, both fields, using some local variables. So because this is an atomic execution, we would hope that T2 will see either the state before the whole thing happens with thread T1 or after. So it either will see the values 0, 0 in the fields, or it will see the values 9 and 7 in the fields. So let's see how this is going to proceed. We'll start with thread T1 reading a value from field X of object foo. And what happens then is we record a version number that's associated at this point with this object, which is in its transaction record, which is shaded blue, and it's 3. Then we have the same thing, or analogous thing happening for thread T2. It's reading a field x from object bar. And the version number that's associated with this object is 5. So it records this value in the read set. Thread T1 then performs write to the field of object bar, and then multiple things happen. So one thing is that it has to, this thread has to record the version number that's associated with this object at the point of write, and you'll see why. Later on, obviously. And then it has to update the value, it has to update the undo information to be able to potentially roll back this transaction at a later point. So it's essentially recording what's in this object in this field at this point. So the value is 0. Then it can acquire, then it can modify the field because it just copied the value from object foo, and acquires a log. So it puts its own transaction descriptor T1, which is, yeah, obviously this is just an abstraction of transaction descriptor. But it puts its transaction descriptor into the transaction record to indicate that this object is now exclusively logged by transaction 1. At this point, when thread T2 is trying to read from the same object, it will encounter the log that has already been acquired by transaction T1, and it will have to wait. Thread T1, in the meantime, can proceed. It will read from object foo again, and it doesn't have to. No, actually, it does record. It does record the version number for the field of this object, which is still 3. And then we will write to object bar, which again means that it has to update the undo information. It doesn't have to update the write set just because this object is already logged by that transaction. So there is no need to do that. And at this point, thread T2 or transactional thread T2 can proceed to its commit. At this point, we'll perform a validation. So we'll have to compare the version numbers for the object that this transaction has read with the actual version numbers that exist in the main memory at this point. And we do that. They're the same, which means that T1 can successfully commit. At this point, it will release the log, updating the version number to indicate that the values in this object have actually changed as a result of a commit, which will make the thread T2 resume its execution. It no longer has to wait on the log. And the data structures are no longer relevant for thread T1. And thread T2 can proceed to read from another field of object bar, recording the version number. This time it's a different version number, obviously, in its read set. And then thread T2 gets to the point when it's trying to commit its transaction. And it also compares the values from read set to the write set, but this time they're different. So this means that another thread in the meantime has updated this object while T2's transaction was in flight. That indicates that there was a conflict and transaction T2 has to be aborted. Yes?
How large are your version numbers? Is it possible that so many transactions commit that it reaches random fetch?
They are essentially 31-bit. They're 31-bit values. So it's. Oh, I'm sorry. Yes, thank you. The question was whether it's a problem. The size of the version, the size of the field that contains the version number is a problem because of the potential for overflow. And obviously, this is a possibility, but it's large enough that we actually don't do anything about it.
By the time you get back around to 0, everybody else will have lost 0.
But yes, but still, theoretically, this, some bizarre workload could potentially make it to break. But I probably should have said this before. We're actually sort of a research lab, so this is a prototype. It's not, it's not anything that will happen anytime soon, at least, in a like Intel product or anything. So this is all researchy stuff. Yes.
Does it look like this can support nested transactions?
Actually, we do support nested transactions. We support closed nested transactions. Actually, we do support both types. But for closed nesting, what we do is that because we have sequential. Oh, sorry, I should have repeated the question. It doesn't seem like this supports nested closed nest, like the system supports nested transactions. And my answer is that we indeed do support closed nesting, and actually recently also open nesting. And the way it's done, so I'm not sure what would be the problem. The undo procedure, or in general. So the way we do it, we have the notion of a memento. So at the point when we start a nested transaction, we remember a certain state of this transaction and an additional metadata structure that's called a memento. And this, for example, contains a pointer to the undo log at the point when the nested transaction started. So essentially, the undo procedure will be able to roll back just to the point of this snapshot, of this memento being taken, rather than to the beginning of the transaction. And so this allows us to just sort of selectively just roll back the effects of the nested transaction rather than to roll back the whole thing. Yes?
So that probably it's not going to happen in Java, but I was wondering what happened since you support C, if there is a DMA transaction while you have a synchronous read.
I'm sorry.
About DMA transactions in C and C++. So the question is effectively about I/O.
Oh, so the question is about how to handle I/O? Yeah. This is a very interesting problem. And in Java, as you say, it's somewhat simpler, just because the interface between the virtual machine and the operating system is rather well defined. So you can play all sorts of games. I have to say that we actually do not have a great answer for the C case, because well, you just don't have exactly everything is done through the library. So it's difficult to determine that an operation that you're performing at this point is going to be really dangerous in the sense that it's going to corrupt some data structure or write to a channel or something like that. So the best we can do right now is we can prevent these operations from being re-executed. So we can make a transaction that is about to perform an operation like that, which we would have to know that this is the operation that we want to handle that way. But we can prevent this transaction from re-executing itself. Essentially, it's becoming an Uber transaction. And everybody else that will try to conflict with that transaction will abort. But that doesn't necessarily mean that we're getting rid of all the isolation-related problems, because this transaction can still write to a channel that a non-transactional code can read. And so this is really all very dangerous, if you will. So yes, the short answer is, I suppose, we have partial solution, but not the full solution to that.
Another question about rolling back. So you keep data about the memory state, so you can roll back the memory state. What about register? Well, during your computation, you load value to register, and if you see a conflict, you want to roll back to the previous point
Yes.
of consistent state.
So in Java, you just have to keep track of. So I think it's done at a slightly higher level, at least in the case of Java. So essentially, you remember the values of the local variables, and so yes, you have to restore them at the point to the same state they were at the point when you started the transaction. Yes.
Are you going to give a slide showing what happens when the fields X and Y are in two different bar objects?
If they were in two different bar objects,
then it would no longer be atomic as far as that T2 could see one of the changes from T1 and not the other.
Yes, but so you say that the update of so the question was, what if fields X and Y were in different bar objects? So essentially, we'd have three objects in here, and all three objects would be used within the the T1's atomic, and all three objects would be used in T2's atomic. Well, we would just have another object that would be locked at the point of update to that field, right?
Right, but T2 would internally see bar of X from which has been updated, and bar 2.y which has not been updated, and if as a result of it is through an exception.
Yes, it's the only one. It would be sufficient for it to see just one field of one of the objects that has been updated by T1 to abort. So it cannot see anything that happened in T1. I'm not sure if this answers the question.
Not the way you describe the sequence, because suppose it already read, yes, it would abort at the end, but suppose that the data was so inconsistent that it blew up before it got to the end. It threw an exception or something.
Now I understand. So the question is, what if an execution that is invalid in the sense of the atomicity property leads to let's say, an object, a field of an object being nullified when it's not expected that this transaction will see a null in this field ever. And this is the result of, let's say, a value that's visible because it has been updated but not committed. So it will be rolled back, but in the meantime, the thread has seen a value null and it throws a null pointer exception, right? That's sort of the scenario.
Or it tries to allocate an object that's just 10 terabytes long.
I don't think we have any special mechanism to handle that. I mean, so, okay, let me think about that.
You don't trap exceptions coming out of the transaction?
No, we do handle exceptions that happen in transactions, and in our case, you actually
That's regular control flow.
yes, you actually commit a transaction. So this is actually a somewhat sensitive aspect of the exception handling is a somewhat sensitive aspect of this whole semantics. So what we do, and that's probably deviating from your question, but maybe we can take it offline. I'd be more than happy to talk about it because now I'm not sure which question I should answer.
You're sort of diverging and probably should take the question off.
Yes. So let's take the question offline. I just say really quickly that we commit on exceptions. So essentially, I don't think we do anything special. We would just say, an exception happened, commit a transaction, and if this exception is not being caught, then it will cause a problem, right? So there's.
So if you do that, then I don't know how to program in this model because I would see partial transactions.
I mean, certainly in C, it'd be a big problem.
Yeah, I agree. I agree. I have to say, I have to think about it a little more, and so hopefully by the end of the talk, I'll be able to give you a better answer. I think there was another question, but maybe it was not anymore. So now I'll talk a little bit about how to make this a little more efficient, because this simple translation that you see over here, it's sort of intuitive, and that's how most of the systems have done it, but it's not necessarily the most efficient one. So we have these operations that nicely abstract these transactional wrappers around memory accesses, but it's, again, not necessarily the best solution because there is some redundancy within these operations that can be eliminated. So this is just an example of what you can do to make this go a little faster, and this actually indeed makes the whole thing go a little faster, or a lot faster. So essentially, we split the operations on data accesses into more fine-grained, if you will. So instead of having these coarse-grained open for write and these coarse-grained transaction write and transaction read, we have open for write, open for read, and log, which are separating the sort of functionality that was enclosed in these transactions previously. And what it allows us to do is it allows us to eliminate some of the operations that we had to perform previously at every data access. So we expose the redundancies, and for example, we don't have to log the object foo every time we access it. It's enough when we do it once, and that's exactly what the what the TM open for write do. It just logs an object, so we can do it once, and the compiler can sort of people optimize away everything else. We also don't have to then open for read because we've already acquired a lock for this object, so it's ours. We really don't have to worry that this read is going to get invalidated because we're writing to it, and nobody else is going to be able to get to it. And we can also eliminate at least some of the logging operations. So essentially, this big chunk of code that we've seen before can be abbreviated to something a lot shorter and a lot cheaper. And this is just an example of an optimization. There are others. We adapted some of the standard optimizations that already existed in the compiler infrastructure. There were some relatively minor modifications. Most interesting ones were due to nesting, because you cannot, let's say, eliminate some of the redundancies across nesting levels just because of these partial rollbacks that we would like to support. So you cannot just eliminate logging operation, let's say, on the nested, undo logging operation on the in the nested scope if you ever want to roll back to the nested transaction start. But we have also some other transaction-specific optimizations. We try to detect immutable data, immutable classes, immutable fields, and we don't have to insert those barriers, those tracking operations for them. Also, if something is completely transaction local and never escapes the scope of a transaction, we also don't have to do it. So that allows us to eliminate some other redundancies. The barrier in this context, it just means those extra memory operations that the transaction memory system is inserting for every data access. And we also do inlining of the fast paths of these operations, just sort of a standard technique, obviously, to make it go faster. But these are the optimization effects. I'm showing just this very selective workloads. We have a lot more data in some of our papers. I'm not going to present them here because that was just supposed to be a sort of an overview. But you can see in here that while we still have a lot, about 30% overhead over the case when there is no concurrency control. In the most optimized case, well, actually it's about 40%, it brings us down quite a bit from about 80% overhead, which is still pretty good because other transactional memory systems that we were aware of, they had, in single-threaded case, they had much higher overheads, on the order of like twice as slow. So we consider that to be a pretty good single-threaded result. But obviously, since you have all these tracking operations, you have to expect that you'll be paying some cost in this case. So the question is whether you get it back in the scalability and performance for multi-threaded workloads when you actually have physical parallelism. So this is, again, just an example of, I'm coming back sort of to the roots, the beginning of this talk, when I presented this example of the hash table. That has undergone a certain number of refinements with locks in mind, and then we've implemented it also with atomics. So we have four types here. We have unsafe, which is essentially no synchronization whatsoever. We have synchronized, which is just regular Java synchronized wrapper. Concurrent, which is this fine-grained, optimized implementation using still logs. And our atomic implementation, which is just, again, simple wrapper. So it's essentially the same as bullet 2, but using atomics rather than synchronized. And for 100% reads, we are actually worse than the concurrent refined log-based implementation, but we scale pretty well, unlike the standard synchronized version, which is not scaling very well. The speed up is not constant. But when we throw some writes into the picture, then the concurrent hash map, the log-based version, is suddenly not doing so well anymore, and our simple atomic version is still scaling quite good. I think I don't have all that much time, right? About 10 minutes. So I think that's about what I need. So there is still these single-threaded overheads. And we're just trying to figure out what to do with them and whether we can optimize them away using some other mechanisms. And one of them, an obvious sort of solution to think about would be hardware acceleration. So this slide presents sort of the foundation for what we try to do with respect to hardware acceleration, which is what are the major overheads of software transactional memory. So that's the transactional memory system that's done entirely in software. And it's you can tell that it's mostly the overhead is in, yes?
Does the overhead come only from within the atomic transactions, or do you have to instrument all of your code to notify whenever it writes anything?
No, this is just the overhead of the actual transactional execution. So the question was whether the overhead comes from instrumenting all code or just the one that's sort of you running the actual transaction, the actual atomics. So this is actually very, in this case, we only insert this, the overhead is confined only to the transactional code. So we don't insert those barriers tracking operations on, for this particular example, on the non-transactional code because we're doing the weak atomicity thing that I talked about before.
So if the non-transaction code writes to a variable which is used from within an atomic transaction, it's...
Yes, transaction will see that value. The transaction will see that value. That's exactly why I introduced this weak and strong atomicity notions, because essentially most of the systems that are currently implementing weak atomicity. And I agree this is probably not the best or not the most intuitive programming model, but the overheads that are related to strong atomicity are still relatively high. So it was, it's an interesting trade-off. And we are actually leaning towards trying to push the strong atomicity model, which is, has everything isolated from everything else. But we were able to get better results only recently with respect to optimizations and bringing down the overheads. So this data is actually based on the weak atomicity model. When there's no overhead on non-transactional code, but at the same time you have weaker guarantees with respect to what transactions can or cannot see. And most of the overhead comes from the read barriers, the operations that are used to track the read operations, and from actual validation of these read operations that happens at commit. I'll talk about how we propose to deal with that, but before I wanted to just give you one slide overview of what hardware transactional memory proposals are around. And so the major one is the sort of traditional hardware transactional memory, HTM, which is a somewhat restricted system in the sense that it allows to execution of transactions very fast, but as long as they're cache resident. So on a physically parallel machine, if your transaction operates data that fits entirely in your cache, and this cache gets never invalidated by any other thread, then it has been isolated. So you don't have to do anything. You can commit the transaction and live happily ever after. But this obviously is very restrictive because really it's difficult to encode any more interesting transactional semantics, like open nesting, closed nesting, what they really mean in this context. And also, it restricts the size of transactions quite seriously because, well, they're restricted to the size of the cache that the machine has. So what has been proposed next is a hybrid, which essentially says, if your transaction is simple and small enough, you execute using hardware, but if you fail, you can always fall back on software, in which case you can handle arbitrary size and arbitrary semantics. But that has a particular, yes?
Oh, yeah.
Yes, thank you very much. Yes, absolutely. So yes, that first execution uses HTM, the second execution uses STM. And the downside of this particular approach is that you still can accelerate only transactions that are very restricted. So the ones that have arbitrary size and semantics, they're still going to be executed purely in software. So that's where sort of we come in our idea, which is to rather than baking the semantics of a transaction or putting restrictions on the size of a transaction and putting in all the hardware, we propose to eliminate these overheads that we think are the most serious ones in the transactional execution using hardware support. And we call it HASTM, which is hardware accelerated software transactional memory. And the idea is rather simple. We would like to have support for marking of blocks in the cache lines. And so a thread can actually claim the ownership of a cache line. And it can query whether it still owns this cache line, but the other threads can actually come in and validate that cache line and invalidate the mark bit so that the thread will be aware that it's not owning it anymore. And that gives us the ability to implement a powerful filter in software. Essentially, these two questions can be very cheaply answered. So, have I accessed this location before? Has anyone in the meantime modified it from the time I accessed up till now? Yes, I guess maybe that's a little redundant, but that's essentially the question that we would like to answer. Yes.
Do you know how this differs from the load to store with reservation capability on PowerPCs? Okay.
No. Yes. Oh, okay. I thought that was a question from there. So this is a proposed set of extensions to the instruction set architecture, and it's just the names of the methods essentially that would be used from the code to mark these bits, query those bits, and reset all the bits, which would be needed to implement the algorithm, which I'm going to very briefly describe on the next slide. So yeah, we do support, because we eliminate only those sort of very generic overheads. we support arbitrary transaction semantics, because we're only telling you that you'll be able to reduce the overhead of the validation, and you'll be able to reduce the overhead of or eliminate the redundancy in the read barriers. And that support allows us to shrink the size of the code for the read access tracking operation from 12 instructions to 2 instructions. This is Intel assembly instructions. And this, yes? No? OK. This allows us also to execute transactions in this hybrid transaction memory mode, as described before, because if we can tell that none of the cache lines, none of the data that we've accessed has been invalidated, and in this case, we can completely skip the validation procedure, and we can also completely skip the read barrier operations, essentially having the same solution as hybrid transaction memory. So this we call aggressive mode, because that can fail, just because we rely on nobody actually accessing this data at the same time. And there's a small optimization that you can reuse those bits across the transaction boundaries. But I think that's about it. And this slide, this set of numbers describes how much this HostTM acceleration reduces the overheads in the single-threaded case. And it's on the order of 30–40% at least. Yes?
So I was going to ask how you anticipate handling cache evictions. Do you just force that to the software model?
So the question is, how do we anticipate handling cache evictions? So if I understand it correctly, so you are asking what happens if you are running in the aggressive mode? Yeah, so since this is essentially the same thing as the hybrid TM that I very briefly described before, the handling is essentially the same, which is if anything goes wrong, you have to re-execute the whole transaction, because it's only at the end when you realize that, or actually it's at the point when the cache gets evicted when you realize that something went wrong, but it's too late. So you have to essentially re-execute the whole transaction in the aggressive mode. And in the non-aggressive mode, the eviction of the cache line results in all those mark bits being reset. So when you get to the end of the transaction and you try to perform commit, you realize that some of the data that you've accessed before has been accessed by other threads because the cache line has been evicted. And so you are obligated to perform a full-scale validation procedure. So go all through these version numbers and compare them with what you have in your read set. So compare what you have in your read set with what you have in the memory. And then you can still commit, but obviously that takes time. So ideal situation is when you get to the end and none of your mark bits have been invalidated by cache line evictions, and then you can say, I'm done.
I guess I'm thinking that, well, if you think about a C case, if you don't have an interpreter underneath you so that you've actually generated a code, which is presumably using one model or the other, then falling back from the aggressive form to the other form implies having that other form of code somewhere, right?
Yes, no, the barrier has to have the actual data, the transactional wrapper around data access operation has to have the ability to dispatch between between the two different modes, right? But in the case, so it's only, I think this is only the problem when you run the aggressive mode, you actually don't execute the barriers because you assume that nothing is going to happen. So it's only when you have the non-aggressive case, when we basically say, okay, I'm checking the bit. If I already own this cache line, I don't have to do much more than that. I can just return and read the value. If I do not own that bit, then I have to record the version number and go ahead and wait until commit time to decide whether I'm still valid or not. So there is obviously the conditional there, but that's how it's handled. So again, the overheads are already reduced by at least 30–40% with respect to the software transaction memory. And these are the numbers for actually that are coming from our simulator, and where this set of ISA new set of ISA instructions have been implemented. And it shows how these things scale on from 1 to 2 cores. And the hybrid TM is, again, it's just this mode when you essentially, once you lose a cache line, you're dead. So that's why it occasionally scales even worse than the software transaction memory, because you just have to redo. You not only waste, so you have to do the same thing that the software transaction memory has to do later on, but you waste time while executing in this hybrid TM mode. So essentially, the bottom line of this slide, and the next slide is that the hasTM scales better than all the other schemes. And that's the end of my talk. As a conclusion, I just wanted to say that we believe that this may be a valid alternative for programming with locks. And the STM still, the pure STM scales pretty well, but there are still overheads that would be nice. It would be nice if we could reduce, and therefore we need some sort of efficient and general purpose hardware acceleration. And so we're working on all aspects of the system, and hope to get better and better results as the time elapses. So thank you very much, and I can obviously take more questions. Yes.
How do you solve the long transaction problem? Let's say I have a number of accounts which keep changing, and I want to have a transaction which gives me an atomic total of all of them at one point in time. That transaction will keep getting killed by the short one forever.
I agree. So there are. Oh, thank you. The question is, how do we handle long-lasting transactions? Transactions that would essentially operate in the background, or essentially long transactions that could be preempted by short-running transactions and therefore be killed every time they try to run for an extended period of time. That's correct, right? So there is no ideal solution, but we're working on at least two. So one of them is it's more or less sort of contention management related. So I mentioned that before. It's to try and make this transaction at some point when you perhaps when you're able to decide, let's say based on dynamic profiling and contention manager or something like that, that this transaction really has to finish now, because it's been re-executed so many times that it's ridiculous. So we make this transaction revocable. So essentially, if there are other transactions that are independent with respect to their data set from this transaction, they'll still be able to execute in the system. But anything that would try to abort this long-running transaction, it would essentially bounce off it and would get aborted itself, which would allow us to once and for all commit that long-running transaction. And that obviously has its downsides. You probably limit concurrency in the system in general by doing that, especially if this transaction is really, really long. But this is a viable option, for example, for if you have a data structure that needs restructuring, like rehashing of a hash table or rebalancing of a tree. Then you may want to just say, okay, just make this rebalancing happen and be done with it. And you don't have to necessarily limit concurrency in the other parts of the system just because you want to rebalance that tree. Another solution is to try and use open transactions, which are a very dangerous construct in some sense for an everyday programmer, but can be a very powerful construct for an experienced programmer. And what that allows you to do is it allows you to relax isolation of transaction in a controllable, semi-controllable fashion. And there's a whole model that sort of comes behind it, but the bottom line is that in the middle of the transaction, you can have a piece of computation that you can say, I committed, and I'm willing to say that this part of computation will be visible outside of this transaction to others, but I'll have a mechanism at the higher abstraction level that will be able to restore invariance in case the big outer transaction is getting aborted. And so what it lets you to do is let's say it lets you update a counter in a long-running transaction on which everybody else would contend and block while you're still running. And obviously, again, you have to take care of the situation when this long-running transaction gets aborted. This counter is exposed. So what do you do? But there are handlers that the programmer can program that will help you restore these invariants at the higher level. But again, these are very sort of researchy ideas at this point. There is no one fixed set of solutions for that problem yet. But it's a very interesting problem. Well, thank you very much.
you.